Welcome to another unit of the ISM course in Statistics 2. This time with a unit on probability theory. Here in this context we basically continue from what we learned about in a unit on set theory with the idea that we can say, well, the sample space, that's all the possible outcomes. So if I have a set M, that's all the specific outcomes I might be interested in. And then, well, if I just calculate how many elements M contains versus how many elements the sample space contains, I will always get a result which is somewhere between 0 and 1. So if the set contains nothing, no elements, it's an empty set, so it's 0 elements. If it contains all the elements of the sample space, it will be 1. And well, so we have a number, percentage of how many events I cover with my set. And well, that's more or less how likely these events are. Because, well, if I consider which of my elements qualify for the conditions which I set, that's more or less what I said, what's the probability of getting one of these elements, getting one of these events to actually occur. So that's our definition for probability. Then we can start make this a bit more complex. For this, we start with a simple starting condition. And well, here we consider two events in a row. First is event A. And well, then we have the chance that either A happens, that's P of A, so P of stands for probability for A, or it's P of the complement of A, so A is not happening. Because there's only these two possibilities, either A takes place, A does not take place. Well, once A has taken place, we are either at A or the complement of A. So far, so good. But then we have a second event. That's the event B. And well, if we are already at A, we know we are at A. So under the assumption that we already have arrived at A, what is the probability of B happening or B not happening? And that's what we call conditional probabilities. So we already arrived at A. So we already had the chance that A happened, despite there being a possibility of it not happening. So under the assumption that it happened, what is the possibility that B happens? So that's the first, the upper one. That's probability of B. Then the vertical line. That means under the assumption that A already happened. Or the lower one of B not happening under the assumption that A already happened. The same thing we can do for the part below, so for A not having happened. Here we get again probability of B under the assumption that A did not happen, and probability of B under the assumption that A did not happen. This gives us the following four outcomes. In both cases, either B happens or B does not happen. And well, if we take all of this together, the chance of A and B happening, that's more or less the intersection of two sets, A and B, and the probability thereof. So here, if A and B happen, we get probability of the intersection of A and B. If A happens but B does not happen, that's the intersection of A and not B, so the complement of B. And the same thing down for the fact where A did not happen, but B happens, or both of them did not happen. The interesting thing about this is that, well, if we consider the probability of A and not A, so the first two lines, they add up to 1. The same goes for the two conditional probabilities of B under the condition A and not B under the condition of A. And finally, this also goes for the 4 final results on the right. So all the 4 results add up to 100%, meaning there's 100% chance that I will get any of the 4 results. Well, makes sense, because after I go both steps, both events happen, I have to turn out at any one of those 4 outcomes, because there's nothing else where I could end up with. Well, this already helps us quite a lot, because this gives rise to the first theorem we consider here. And that's the so-called multiplication theorem. This simply states that the probability of A intersects B, so both of them having happened already, is nothing else than the probability of A under the condition that B happened times the probability of B. So you basically go one of the different branches of the tree from the slide before and multiply up all the probabilities on the partial branches. And then we get of all of them happening at the same time. This, however, is the more general version. If I have a simpler situation where A and B basically do not have anything to do with each other, that's the proverbial sack of rice which falls over. Well, butterflies effects aside, if somewhere on the other side of the world a set of rice falls over, this will not impact anything here at all. So the event, sack of rice falls down, and for example, me winning the lottery are not related in any which way. So if I then want to know what the probability is of both events happening at the same time, I'm not needing the conditional probability, because if I have 2 events which have nothing to do with each other, I can replace the conditional probability of A under the condition B with simply the probability of A. So if the events A and B are so-called stochastically independent events, we're getting back to this phenomenon later on where we have a test to check whether they are actually stochastically independent. If they do not have anything to do with each other, we don't need conditional probabilities. This will simplify the matter immensely. Well, this is rarely the situation, so this is just like the special case, which, however, seldomly happens. So it's always better to go with conditional probabilities. Well, okay, if we have this multiplication theorem, we can take a look at the corresponding example. The probability that a random student passes the math exam is 72%. The probability that he passes both the math and the statistics exam is 54%. Then question, what is the probability that he passes the statistics exam if he already passed the math exam? Well, usually a good way to start with all of this is first write down in mathematical notation what the text tells us. So we take a look, we have 2 numbers here, so we have to write down the numbers in any decent fashion. Well, the first thing is passing the math exam, 72%. So let's call this P of M, M for math exam. That's 0.72, 72%. Then we have the 54%, that's math and statistics. Both are passed. So here we have probability of M intersects, and then S is for passing statistics. And this means both happen. I have passed math, I have passed statistics. The chance of this happening, 54%. Okay, here it doesn't matter if I write like passing math and statistics or passing statistics and math. This follows from also the fact that the intersection is a commutative operator. So it doesn't matter if I go M intersects S or S intersects M. So I can switch this around. Okay, So I have noted the two parts that I have. So what am I looking for? I'm looking here for the probability that I pass statistics. Then it says if he already passed math. So under the assumption that math is passed. So under the condition that. So I'm looking for a conditional probability. Probability of S under the condition that M. And well, for this, we can use the multiplication theorem. I just copied this from the slide before. Here, however, the problem is we first have to solve for the conditional probability. So we divide this by P of B. In our case, we divide this by PM. And well, obviously that's the only value we have. And well, here we get then the probability of M intersects S. That's our 0.54 divided by the probability of M passing math. That's 0.72, giving us then a conditional probability finally of 0.75. So that the chance of 75% of passing statistics when he already passed math. Okay, so basically this covers the example. This also tells us that we can use the multiplication theorem in two ways. Either to get the probability of both of them happened. So A intersects B, or for getting a conditional probability. What is the probability of one event happening, so not have happened yet, of one event happening if the other one already happened? So a multiplication theorem can be used in two ways. Okay, so that's pretty nice, but let's have a look on a different theorem as well. That's the so-called addition theorem. If you watched already the part on the set theory, this is where I get back to this. Because, well, that's the addition theory. This tells us how I calculate the probability if I have the union of two sets. And well, here I just add up the two partial probabilities, so of A and B, and then I subtract the intersection. This is what I mentioned in the unit on set theory. If I won't subtract the intersection, I would count these elements twice. So I skip the second part and go to this graph. So the marked area here, that's the intersection. If I would count all the elements, I would count all the elements in M. Then I would count all the elements in N. And if I add them up, I would have counted the two elements in the intersection twice. Well, that's obviously too much. So that's why I subtract the two elements once from all of this, so that I only have counted them once. Okay, so much for the first formula. What about the second one? Well, if the intersection is empty, and again, the intersection is empty if the two sets are so-called disjunct sets, or if the events represented by those sets have nothing to do with each other. So if they are independent, stochastically independent, then the addition theorem simplifies to probability of one event plus probability of the second event. Well, that's relatively easy. So let's do this as well with a small example. In this example, we have a similar case as before. So we have the probability that a random student passes the math exam is 72%. For the statistics exam, it's 43%. The probability that he passes both the math and the statistics exam is 54%. And then a question, what is the probability that he passes either the statistics exam or the math exam? So once again, we first start by copying all the information from the text. So here first we have probability of passing math, 72%, 0.72. Passing statistics, that's 0.43. And passing both of them, that's again the 0.54. That's the information what we have. now we are asked about that he passes either of them. And the passes either, that's an indicator for using our union, the probability of the union, or an indicator for using the addition theory, which tells us here, well, what does the union stand for? Union stands for passing math, or passing statistics, or passing both of them. So yeah, that's actually what we're looking for. So we can copy the formula for the addition theory. And what we see here, we simply have to add up probability of passing math, probability of passing statistics, so 0.72 plus 0.43, and then minus both of them happening at the same time, so probability of the intersection of both of them. That's basically here our formula. If we insert our values, we get as a final result 0.61, which means we have a 61% chance of passing either math or statistics or both of them. And well, that was everything for this small example. So let's skip or go on with the next aspect. The next aspect is the so-called law of total probability. Law of total probability, that sounds very fancy. This basically means, and here that's the case for two events, or for one event which can be split up in two disjunct partial events. That's more like a better average of probabilities. So in other words, if I consider this, I can split up one event in either this event happens or doesn't happen. And then I know the probability of some other event in the case that event B does not happen, and I know the probability of this event in the case that B happens. And I want to know what the average chance of this event A happening is. Okay, sounds too strange, sounds too convoluted. Let's take this differently with an example. Imagine you have someone visiting restaurants. You're visiting a restaurant. You have the choice of visiting, let's call this an Italian restaurant or Chinese restaurant. You know how happy you are with your food choice or the food offered. If you go to an Italian restaurant, you know how happy you are if you go to a Chinese restaurant. And now you're simply thinking about, well, what is the overall chance of me being happy independent of where I go having something to eat? So what's the average happiness when I go out having something to eat? And that's where the law of total probability comes into play. This answers basically, if you only know your conditional probabilities, I go to the Chinese guy, my percentage of being happy is this and this high. I go to Italian guy, probability of being happy with my meal is this and this high. I go to the Russian guy, my happiness or chance of happiness is this and this high. And I just want to know, what is my average chance of being happy with my meal when I go out eating somewhere out in a restaurant? That's the law of total probability. That's for two cases. In general, looks a bit more complicated, but it's still the same way to go about this. You always consider the probability of, for example, going to an Italian guy times the probability of being happy when going to the Italian guy, plus the probability of going to a Chinese guy times the probability of being happy when you go to the Chinese guy, to the Italian guy, sorry. Then again, plus the probability of going to a Russian restaurant times the probability of being happy when you go to the Russian restaurant. And again, plus so forth, so forth. So it's basically always the same way to go about this, either in two cases or in how many other cases there are. The only important aspect is here, the cases need to make up all possible situations. So if you go with restaurants, you actually need to consider all different restaurant types which you might be inclined to visit. So in other words, the probabilities of the BI here, if I add up all of them, I need to end up with 1, with 100%. Okay, so much again for the general theory on this law of total probability. Let's have a look at an example to make this perhaps a bit clearer still. So here we have the probability that someone gets to work by car is 36%. 43% of these people are happy about their commute. Of the rest, 56% are happy about the way they commute to work. Our task now, calculate the total probability of someone being happy about their commute in general. Okay, what are we going to do? As I said before, we simply start by noting the numbers we are given in the text. So we have here the probability of commuting by car, that's 0.36. Thereby, the probability of not commuting by car is 0.64. We also know that of all the people which go by car, 43% are happy. So that's basically probability of being happy under the condition I'm going by car. Well, if I have this, I also have the other information that if I do not go by car, I have a probability of 56%, so of 0.56, of being happy. So the probability of being happy under the condition I'm not using the car is 0.56. And then I'm basically asked, what's the probability of being happy? That's here, probability of age. Okay, for this, I'm using the formula for the law of total probability. This, in our case here, looks as follows. So I go with the two partial probabilities, and I always multiply them with the probability of this particular event happening, which before has been the condition. If you really think about this, what we're doing here is, if you think back on the very first slide we had this tree, and in the end we said that the probability of two events happening at the same time, that's basically conditional probability times the probability of the event which is the condition, and both of them multiplied. We're doing the same thing here. So we're basically summing up all the different probabilities of the intersections of both events. Okay, so much as a background here. In this example, we simply plug the info we have into the formula, and we get as a result 0.5132. So the percentage of being happy, independent of in which way you commute to work, is 51.32%. And well, that's then already there is to this exercise, or to this small example, and we are only left with one theoretical part. That's the so-called Theorem of Bayes. This looks as follows, or in general terms, in other words, like this, or in general terms, like this. Okay, this looks relatively complex. What does this actually tell us? Well, this more or less tells us what happens if we switch around the thing what we are interested in with the probability and the condition. So here we have first on the left side, in the first line, probability of A under the condition B. What if instead I'm interested in the probability of B under the condition A? And then I'm basically turning this around. The formula, the second formula, only looks a bit more complex because here I combined the theorem in the first line with the law of total probability. So what we have below the fraction line here is nothing else than the probability of A written via what we got for the law of total probability. So if you just want to know what the opposite probability is, I call this opposite, it's still a conditional probability, but with first event and second event switched, that's where you can use the theorem of Bayes. You could even go so far and say, well, what if I have this in more than 2 cases? Then we get the general version. So here I'm just again switching this around. I before had A under the condition BK. So as I said before, for example, being happy under the condition of taking this and this way to work. If I now turn this around, I would get the probability of taking a car if I'm happy. Probability of going by train if I know I'm happy. That's basically switching one conditional probability into another. Okay, maybe this becomes a bit more clearer once we take a look at an example. So here we have Peter has read 66% of the books written by a specific author. Of all the books that he ever read, 79% he liked. Books from this specific author he likes with a probability of 93%. My question is, what is the probability that if he likes a book, that book is also by this specific author? Again, we just note all the information we have from the text. First off, we know the probability of having a book by this specific author, 66%. The probability of liking any of the books, 79%. And under the condition that this book is from the specific author, he likes it with a probability of 93%. And now we're basically asking, what about the opposite conditional probability? What about assuming he likes the book? What are the chances the book is from the specific author? For this, we're using here Theorem of Bayes, but we're going to divide this by the P of B, or in our case, P of L. Then we just insert our values here. That's the 3 parts we have from the exercise, and calculate this as a probability of 77.7%. So the chance of the book being from the specific author, if he only knows he likes the book, are 77.7%. And well, that's all to this exercise. And that's also all there is to this unit on probability theory. So we covered quite a lot of stuff. I hope you still enjoyed listening to it. And if you're looking for additional units in statistics too, feel free to visit the rest of the course or have a look at the corresponding playlist. I say goodbye and see you next time.